Hello, my name is Sophia Schwartz, and welcome to the STEM with Friends podcast, where I discuss a variety of science topics with interesting guests. I hope you enjoy it.
We were never about doing everything we had to do in-house. We did only the things that only we could do in-house.
Okay, yeah.
And things that others could do better than we could, or at least as well as we could, we would send out. So we in-house were about 22 people. But we had FTEs all around the world doing work for us. So we would have, let's say at one time we had 7 or 8 in Canada doing medicinal chemistry. We would send, so actually here, I'll even give you a sense of kind of what a design test cycle for a molecule looks like. So these Canadian medicinal chemists would design molecules. We would then have a small amount shipped to WuXi in China and a small amount shipped to us. We would run the primary pharmacology assays to say, hey, yes, this molecule is still activating PINK1, or it's getting more potent, less potent, et cetera, versus the prior series. In WuXi, they would start looking at pharmacokinetics. Whoa, the microphone's dropping. So, I think something that you really have to keep in mind when you're making drugs is it's not just about, can I get really good activity on my target? A small molecule drug, especially one that's taken orally and is brain penetrant, has to check so many boxes. It has to be metabolically stable, so the liver can't just destroy it the second it goes through first pass metabolism. It has to be permeable because it has to, get through membranes. It has to be reasonably soluble so it dissolves in the gut and is available to go through membranes. It has to be blood-brain penetrant, so it can't have high PGP. There's all this stuff that you have to cram into one molecule. And so you can imagine, looking at all these things and kind of staging out what we called a cascade of assays. You'd put, let's say, 20 or 30 molecules in the top, and you'd fail out half of them, and then you'd run another set of assays, you'd fail out another third. And what you hope for is that by the end you have something that looks more drug-like than the last number of molecules. And just to give you a final sense of this, I'm not going to give precise numbers because somehow I feel that would be proprietary information. We made more than 1,000 molecules.
Oh, wow.
Over the course of our program. Well more than. And we spent, maybe I can't say that, but we spent a lot.
We spent a lot.
We spent a lot of money. And just to kind of put a finer point on this, we got to a pretty exciting lead molecule that was suitable for doing good biology work and kind of doing some initial proof of concept in vivo, et cetera, after about $4 or $5 million of spending.
Oh, wow.
Wow.
It took a lot more than that to get to a molecule that was worth putting into a being.
How did you break through that frustration of having to test so many different molecules until getting to something?
It's worse than that, though. It's worse. Because, here's
frustration isn't the right word.
Yeah, no, because here's the crazy thing, right? It's like running through a minefield with a blindfold on. One of my mentors, he's been in all sides of the business. He had management positions at Warner Lambert, Pfizer, and then he ran a biotech company, one less successfully, one very successfully, and is now a venture partner at a VC. Great guy, and has just seen everything. He describes it as the great unveiling. Right, because as I was saying, with a molecule, you put it in the top, and does it keep making it, keep making it, and as you put it forward further and further into this great unveiling, the assays get more expensive, and it's more time, and you think you're golden. It's like the end is in sight, and suddenly you step on something, and boom. The molecule's dead. You cannot take it further because you've tripped some fundamental liability that no pharma is going to look at and say, I want to develop that. And then you're back
to where you started.
Yeah, so we had this happen, and it's normal. I'm not saying that this is a normal thing to happen in drug discovery, but you want to know why it's so damn expensive. It's because this sort of thing happens, and then your next molecule up is 6 to 8 months behind, and, $3 to $4 million in research spending behind. Meanwhile, you still have your whole staff, doing their experiments. So that's a lot of overhead. So drug discovery is hard.
How long did it take from the beginning of the company to the
10 years.
10 years. Wow. And a whole lot of money.
And it has another 9 to go to get to the point where it's going to
clinical trials.
Yeah, right. 9 would be my very ballparky estimate. At this point, it's in the very capable hands of a global pharma company. But I would say it will probably be very close to a decade to get this drug.
So how do you envision this drug molecule impacting the lives of people with Parkinson's?
So the really brutal thing, and this is true of Parkinson's, this is true of ALS, this is mostly true about Alzheimer's. I don't know how sanguine you want to be about the recently approved antibody-based therapies, but mostly they're not having a huge impact on disease progression. And the reality is, if you're diagnosed with Parkinson's, you can actually manage your symptoms a lot better than you can for some of those other diseases. You can take synthetic dopamine precursors that can be metabolized into dopamine in the body, and so you can kind of add more dopamine to the system that way and kind of overcome some of that deficit. Bear in mind, by the time you've been diagnosed with Parkinson's, you've lost between a half and 2/3 of your dopaminergic neurons.
Wow.
In the substantia nigra in your brain. So the problem with that, though, is that over some length of time, it varies patient to patient, but over 10, 15 years of your disease, those neurons keep dying. And at some point, you stop being responsive to the L-DOPA. You stop, the symptomatic therapies fail just because you don't have dopaminergic neurons left to do the work. And end-stage Parkinson's is rough. I mean, there are a lot of comorbidities, dementia, psychosis, etc. So we hope that before our drug is approved, other drugs are approved that are disease modifying. But we hope to live in a world where there are disease modifying therapies, where that rather than, declining over 10 or 15 years and it getting to end stage disease, that we can stabilize you, or at least dramatically change the rate of progression such that you never hit end stage disease. You're 89 years old, you have a well-managed disease for the last 25 years, and you die of other causes, never having reached end stage Parkinson's. So that was our objective. It's like let's change the path of your disease so that the progression is much less.
Yeah. Say I was my grandfather has Parkinson's disease. Would I have to start taking this pill when I'm young? Is it a long term?
That's an excellent question.
Yeah.
That's an excellent question because if you're already in end stage Parkinson's, there's nothing to save.
There's nothing else.
There's nothing to save. So yes, what you're saying is right, which is that a therapeutic like ours is really going to be of greatest benefit to people who are early in the course of their disease.
Yeah. And do you think that this drug would be covered by insurance?
Oh, yeah. Yeah, I mean, it's very, very unusual for a drug not to be covered by insurance.
So around what age group, or does it not matter the age group, just the time you develop the disease?
That's right.
Yeah.
That's right.
So is it the age group, the time that you develop the disease, it's different for all people? Or is there relative?
I mean, it's extremely uncommon for somebody to be diagnosed with idiopathic Parkinson's at 35.
Yeah.
It is a disease of aging. Most Parkinson's diagnoses will happen after age 60. That doesn't necessarily mean that all of them will, and certainly people do get diagnosed in their 50s. But again, the younger you are, the less likely it is you have idiopathic disease. If you get Parkinson's at 30-something, you should get genotyped because you may very well have a familial form.
Yeah. How much does the drug cost the company make, if you could say that?
Well, no, I mean, that's a problem for the commercial side of AbbVie. 10 years from now. What I can say about drug pricing, and this is sort of more with the economist's hat on than anything having to do with mitochondria specifically. So Parkinson's has an economic burden associated with it. You can imagine that not only does it incapacitate the person with the disease, but it creates a lot of requirements around caregiving. It takes time from the family. I don't mean to sound, kind of ghoulish about this. Like, oh, it's just money. No. I mean, but realistically, there are costs associated with keeping these people in the best health you can, and the time that families and other caregivers, professional caregivers, have to spend in take care of them. So Parkinson's is expensive, on top of all the other horrible things it is. So the Michael J. Fox Foundation estimates that it's about $50 billion a year in the United States.
Wow.
And as these diseases go further and further in their courses, obviously it gets worse and worse and worse, right? So as we said, end-stage Parkinson's has a high incidence of dementia. I think it's 30 to 50%. I would have to go back and check that, but I think that's about the number. Psychosis, 10 to 20% kind of range. Those are bad news, and those are very expensive things to take care of. So you can imagine that if a drug really does alter the progression of Parkinson's disease and allows it to be treatable, via symptomatic therapies for the whole course of the disease or the whole course of somebody's remaining lifespan, you'll alleviate that economic burden a lot. Mm-hmm. And so, does it make sense to have a drug that insurers and others are paying $10+ billion a year for? Well, it depends, but in this case, it probably would. If you're interested in drug pricing and societal benefit and all those other things, you should go check out the case of Hep C of the Harvoni and Sovaldi antivirals. Fascinating case. They pretty much stopped, or like 95, 98%, whatever it was, curable.
Really?
And what would happen to those patients otherwise is they'd be on like a fast track for liver transplants. And that is much more expensive.
Wow. A lot more.